Good. Right there.
Not too bad.
Check 1 2 1 2. Hey hey. Check check 1 2.
One, two, three, 1, 2, 3, 1, 2, 3, 1, 2, 3. Test, test, test. It's okay.
Once it's quiet.
Yeah.
Normal clicker, advance, reverse, and then laser pointer is the red one there.
Okay.
Yep, there you go.
For moving the. So okay.
Yeah, forward and back.
And sorry. Okay. Forward, back, and the laser is.
Laser's red.
Laser is red.
Yep.
Okay. So that's it. Perfect. Great. I don't have the computer because usually it's distracting.
Yeah, sure.
You never. Okay. Yeah.
Okay. This is my introduction for you.
Oh my goodness.
Well, I won't bring it over here.
This is the D-Cubes effect, you see? People, wow. It's great.
All right. Did you get a water?
Yes.
Okay. go ahead and, you want to have a seat, and I'll go ahead and read this. Like I'm hearing a radio somewhere. Maybe it's in my hearing aid. No, I'm just kidding. All right. Well, welcome to the second day of the 2024 American Gem Trade Association Elevated Seminar Series, sponsored by the American Gem Society. Gemological applications of basic spectroscopy techniques in everyday laboratory practice. Now, this gets my attention. I assume it does yours, which is why you are here. Technological progress in every field has impacted our industry. New synthetics and treatments are posing serious challenges for us as gemological professionals, and an update of knowledge and instrumentation is needed, desperately needed, to prevent expensive and liable mistakes. Unfortunately, the standard techniques and instrumentation that we have used in the past are no longer enough. We can do enough, we can do some at the desk, but there are some instruments that we really do need today. Today we need UV vis NIR, we need FTIR, we need Raman, we need fluorescence spectroscopy. That's not something I came home from GIA with. These are considered standard equipment in gemological laboratories, and in certain cases, even other more advanced instrumentation like EDXRF, LIBS, LAICPMS. I have my laser in the garage. Of course, the instruments themselves are only half the equation. We need a reliable database to help validate the results of our tests, and we need someone who knows how to operate the new equipment. In this session, we get to hear from Alberto Scaraini, an IGI graduate gemologist, appraiser of the Chamber of Commerce, and registered expert of the Tribunal of Rome. Alberto is co-founder with Mikko Ostrom of MAGILABS, a company founded in 2012 that specializes in the manufacturing of advanced gemological instruments. They have developed Raman, UV vis, FTIR, fluorescence spectroscopy, specifically designed for gemology. This is for us. Alberto has been a longtime member of the UNI Commission, the Italian standards nonprofit, specifically focused on the UNI rules about gems and precious metals, and a representative delegate for the development of the bill about gemological materials at the ex-commission of the Chamber of Deputies of the Italian Parliament. Alberto has given seminars and workshops on advanced spectroscopy for GEM-A, the AGA, the HRD, the IGE, and at Rome, Naples, Bari, and Florence universities. Jewelry and gemology author, he is currently one of the editorial directors of Rivista Italiana de Gemologia, the Italian Gemological Review. In 2019, he received, along with Mikko, awarded the AGA's prestigious Bonanno Award for Excellence in Gemology. In 2022, Alberto expanded the operations of MAGILABS by establishing MAGILABS USA in Houston, Texas, and I'm sure you are going to recognize his Texas accent. Please welcome Alberto Scaraini.
Good morning, and thank you all for being here. It will be a very, very long, it will be a huge number of slides, so we have to be very, very fast, because what we are covering, it's a huge amount of knowledge. And of course, we are squeezing this in 1 hour, and I really hope that you will get, especially not only the description of the techniques that are used nowadays in the labs, but mostly what it can be done, what it can be, done with them, in order to identify the material, identify the treatments, the synthetic, and so on, to face all the challenges that we are, having more and more in our, day work. So just start. These are the basic for spectroscopy techniques used in a lab. We have to think that everything we will discuss here today is just the interaction of the electromagnetic waves with our stone, okay, with our gem. So based on the interaction with these waves and our gem, we will understand and we will identify the material, we identify treatments and synthetics. Of course, the electromagnetic waves can be of various types. Let's start with the UV Vis-Near, which actually is the abbreviation of ultraviolet, visible, and near infrared. These are the three fields that are used in this spectroscopy. It's an absorption transmission of the radiation. And of course, the good thing is that you can record the spectrum and compare it to a database in order to check your stones. Then you have Raman and FTIR. They are both vibrational spectroscopy. We will tell you what they are in more details later. They are actually sister technologies. They are always both present in the GEM lab, especially because Raman is dealing far better with very well defined crystal structure, while FTIR is more efficient on amorphous material and organic material. But they are both vibrational spectroscopy. Then we have photoluminescence and fluorescence, and these are emission spectroscopy, like these two, and they are based on the reaction of the stones compared to lasers and strong emission sources. Let's start. Okay, we will cover just a little bit the techniques, because this is not much interesting for you. Probably it's more interesting to understand what you can do with that. Okay, UV Vis-Near is the closest thing to everyone knows, the spectroscope. So the difference between the spectroscope and spectrometer is actually that in the spectroscope you visualize the spectrum. With the spectrometer you can actually see the spectrum on a screen and record it and store it. I mean, leave alone the fact that it's super complex for any of you that use the spectroscope daily. You know how much complex it is to orientate the stone, keep the stone, and what you are seeing is a very, very narrow band of light. So starting to discriminate these, and of course you cannot record anything, you cannot compare anything, so you understand what is the difference and what is the major impact that you have in using a spectrometer instead of a spectroscope. Leave alone the fact that you will have far, far more information. Here I put together a spectrum of a color change zircon, as you can see through your spectroscope, with the spectrum recorded by UV Vis-Near signal as a spectrometer. The first thing that comes to your eye is that here and here you don't have anything. Of course, in the spectroscope, what you can see is only the visible range of your light. Okay, so it starts from 400 nanometers to 700 nanometers. The good news is that the spectrometer can record even other areas, and this means more data for us to be used. So here you have, in this case, this spectrometer starts from 365 nanometers, but there are even others that start even lower in the UV. And then we have the near infrared, which is super useful. For example, we'll see it later, how many nice information and good information we can get. And the nicest thing is that once we get the spectrum, it's there. I mean, we can work with that. We don't have to hold anything together, it's there. We can play with it, and we can compare it to a database of reference that we have. Okay, the problem about stones is generally the problem is the beauty of them. They are cut, but the problem for us is that the cut, it can generate a lot of bouncing of the light rays inside, and so it can be difficult for us to get the absorption light from the stone. Okay, so what is nice for the stone itself, I mean, this nice cut is something super nice for us to see. It can become a complication for the GEM lab. So how, for the UV Vis-Near, we solve this issue. This is one of the systems used, and actually you have an integrating sphere. It means that you have a sphere which is composed of the high reflective material, okay? And then you let the light source entering from this side, and the light is bouncing here and there many times inside this sphere. The stone is put on the bottom of the sphere, and underneath there is the collimator that goes to the spectrometer. That means that the light is entering the stone from every possible direction, and this optimizes the quantity of light that can come out, and at this moment we can read actually the absorption of the stone. So this integration sphere removes the orientation-related errors as a pleochroism and dispersion. As you know, for double refractive stones, it depends by the orientation. You can have slightly different spectra. In this case, no matter how you put the stone, you will have a consistent spectra, which is super useful when you have to build up a database, and compare the database with your result. This is an example of how two diamonds, one type 1A and type 2A, showing up on a spectrometer which is a UV sneer. In this case, you see the red line is a type 2A. It's completely transparent to UV until 200, roughly 220 nanometers, while the type 1A below 340 is completely absorbed. This is already something that can differentiate, the two types of diamonds based only on this technique. What you see here, these are minor peaks. We will talk about them later. This is the entry, is the defect entry of aggregated nitrogen, 3 atoms of nitrogen and one vacancy in natural type 1 stones. This is a composite screenshot of several spectra. They are all pink diamonds, but of very different types. These two in the bottom, they are natural pink diamonds. The pink color for diamonds is due to this band, which is called the pink band at 550 nanometers. So every time you have these spectra, you are practically sure that the diamond is natural and it's untreated. And the color is natural. The pink color that you are seeing is natural. Then you start to see some other spectra which are similar but absolutely not identical to this one. And then you have an HPHT synthetic diamond. You still have this band, but it's not exactly centered in 550 nanometers and not so effective. And then you have a natural irradiated one. Again, you have this band, because actually this is the color that shows up, but it's not the 550 nanometers. And then you have another HPHT synthetic and a CVD, which the silicon vacancy means. This is completely different from anything that you can see in a natural pink diamond. So even with this simple technique, which is not complex, you can actually identify pink diamonds and their, the counterpart, the treated and the synthetic counterpart. Let's go to Ramans. For now, I'm only describing the technology, okay? Raman is, of course, a non-destructive analysis. It's very important for us because we are dealing with precious stuff and we don't want to damage our stone at all. It's super fast for identifying every kind of material, very fast. It doesn't need any preparation, and you can have a result in 20 seconds to 1 minute. You don't have to prepare the stone at all, and what is good is that it works nicely both on polished and rough material, which is a limitation, for example, of the refractometer. And then, you know, when you start gem identification with the standard, you know, gemological tools, I mean, I put these in this order, but everyone has his own order. You know, everyone starts with something different and so on. But you know, the work of gemologists has always been just like a Sherlock Holmes. You're actually working to eliminate clues, you know, until you reach the answer. So you, depending by your skill, but when you have a stone in your hand, you look at that and maybe you have 3, 4, 5 different clues about what it is. And then you start with different techniques, polariscope, refractometer, I mean, you remove all the double refractive or single refractive and so on, until you arrive to the answer. Raman spectroscopy is the only tool actually that can do everything like that with one tool only? And the answer is 100% correct. I mean, there's no possibility when you have, for example, a spectrum like this that you are making an error in the identification. And that means fast, speed. I mean, we need to be fast. I mean, to do these things, I don't know, it depends by everyone's skills, but only the mass with the specific gravity and so on, it takes time. Compared to the 20, 30 seconds that it takes to identify a stone, and think, again, we don't have one stone in the morning to, be done by the afternoon. If you go in the lab, you have hundreds, thousands of these things. And so having something, that can solve you the identification problem in so fast, it's absolutely important. So what is the Raman effect? When a substance is irradiated by a monochromatic source, I will add, a fraction of this radiation is scattered. Most of the scattered radiation will have the same frequency and, of course, the wavelength as the source. And it is called elastic scattering, the Rayleigh scattering, okay? But a small fraction, 1 out of 10 million photons of the scattered radiation, presents different frequencies, so different wavelengths, compared to the source. And the result is an inelastic scattering. And this is the Raman scattering. This is Sir Raman. He made this discovery in 1928. Think about this, with no spectrometer whatsoever. I mean, he was a genius doing that. And for that, he was awarded by the Nobel of Physics in 1930. So the Raman scattering is closely related to the vibration modes of a substance. So not only the chemical composition, but even by the vibration of the molecules. So since these depend on the mass of the atoms, the binding forces and symmetries, it follows that the Raman spectrum of a substance corresponds to its real fingerprint, and it allows it for unambiguous identification. This is fantastic. I mean, for us, it's super. You identify anything with one passage only in a matter of 1 minute. 1 minute, not even 1 minute. And then this is the proof that no matter we have 4 different elements, 4 different material composed essentially by the same element, it's carbon. The fact that their crystal structure is completely different from each other, for example, we have graphite and diamond, it brings that even if they are composed by carbon only, they have different Raman spectra. And so actually, again, we are not talking about only the chemical composition, but how the crystal structure and how the atoms vibrate inside the molecule. And this shows to you the importance of a tool like that. This is a quick screenshot of diamond and hole, or more or less hole, heat simulants. You can see there's no possibility, absolutely no possibility of making any mistake. Diamond is 1 peak only. The easiest Raman spectrum is 1 peak only, 1,332 centimeters minus 1. It's why 1 peak only? Because it's 1 element only. It's only carbon. There's only 1 bonding, and so it's only 1 peak. All the other materials have a completely different Raman spectrum. How technical it works? You have a laser, you have a filter that cleans the laser signal, okay? The laser hits the stone, and the stone, as we said before, generates first a huge elastic scattering. You see the green arrows, they have exactly the same wavelength and frequency of the laser that we are using, and then a very, very tiny portion. That's the reason why the Raman spectroscopy needs to be very, very sensitive, because the signal is minimal. It will have a different frequency and wavelength. At this point, all I can do is to put a filter here that screens out, completely blocks the elastic scattering, and the results will be only the inelastic scattering. I have to measure that, put in a computer, and I will have the result. I mean, it seems easy, it's not so easy. But this is the schematic. Then we go to the confocal micro-Raman spectrometer. This is a very important tool, especially nowadays in the GemLabs, because so far everyone check inclusions inside the stones, okay? And before these instruments was available, you could guess what the inclusion was, because it was embedded, inside the stone. So depending on your skills and so on, but you were actually observing the inclusion, and you will not taking a conclusion, you will take a guess, a good guess maybe, especially if the crystal was not deformed, and well, well grown. Now with the confocal micro-Raman spectrometer, we can actually identify an inclusion inside the stone with 100% certainty. So this is another game changer, especially for the identification of gem association and origin and so on. So how it works, you have a tiny inclusion here, very tiny, probably someone in the audience can identify the stuff itself already, I don't think so, very small. And then what I'm doing is that I'm focusing the microscope of the micro-Raman exactly on this inclusion. This instrument has a spatial resolution of 3 microns. So this is the size that we can, use to check this kind of inclusion, even micro inclusions. I have my screen here, and then I have the actual spectrum, which is this black line. Okay? Then I shot the stone. I forgot to mention that the stone that you saw before, it was a sapphire. It was a blue sapphire, and that inclusion was inside the blue sapphire. So I know that the stone that contains the inclusion is a sapphire. So what I can do is that I will subtract the spectrum of the sapphire from my actual spectrum. Because if I shoot the inclusion, I have to think that the Raman spectrum that I'm getting is a composite spectrum between the host and the hosted material. Okay, sapphire and the unknown inclusion. If I subtract the Raman spectrum of the host, what I have resulting is this one, is only the spectrum of the inclusion that I have, which is checking on my database at zircon. So now I know that that inclusion is at zircon. And this is super helpful. Think about all the possible inclusion that can lead us to not only the identification, but to many other studies about our stones, and can be only done with the confocal micro-Raman. This is a super nice setup from Thomas Einschfang in the GGTL laboratory in Geneva, on Liechtenstein, sorry. It's a photoluminescence spectrometer. How does it work? I'm shooting the stone with a strong emission, usually a laser, okay? And the stone reacts with an emission. I'm measuring this emission, and of course, comparing to a database, I can understand a lot of things about treatments, about the identification too. Thomas was so kind to give to me this, but mostly this, which seems a weird thing, but let's see it here. So we have the range from 400 nanometers to 1000 nanometers. In order to be so precise and having this reading, 448.1, you cannot have only one light source. You need to have multiple light sources that are covering all the spectrum starting from 400 to 1000, because their efficiency based on the wavelength is different. So let's start. This system has 5 different lasers, and you see here the wavelength of the emission. So the 405 is this one. Then it starts at 473, it starts from 473, then 532, and so on. In the end, you are combining all this information, and even if this seems to not telling you anything, this is super important, not only in diamonds, but even in color stone. By the way, that's Thomas Einschfang's fashion. This is one super rare stone. This is a natural diamond with silicon vacancy inclusion. And actually, it's a clean stone. It doesn't, the inclusion, the silicon vacancy defect is not coming from any inclusion or decrepitation of garnet and so on. So this is super, super rare stone. This is one of the very, very, very few exceptions where you can have the silicon vacancy defect in a natural diamond. We are talking about GIA released an article years ago, and out of 70,000 stones, probably there were 9 or 10 stones having this kind of feature. And this is another spectrum. This is what you can see. This is the same stone, and I'm still using the same technique, but I'm freezing my diamond in liquid nitrogen. What I'm showing you here is the difference between the two and how much effective is the red line is the stone immersed in liquid nitrogen comparing to room temperature. Look at here. You have a small bump here, but here this bump developed in a huge peak. Look at the silicon vacancy here. It was a tiny, tiny bump, and here is a huge peak. So it's not a matter of having a nicer peak. It's sometimes you don't see the peak in room temperature. That's the reason why you really need to have liquid nitrogen immersion. This is only for diamond. There are even experiments done on color stones, but they are quite limited. But every time that you see an article about diamonds, talking about peaks in diamond and so on, you can be sure that stone has been immersed in liquid nitrogen before being tested. This is a natural pink diamond versus an HPHT irradiated anneal pink diamond. It's a natural one, HPHT treated. Okay, they are both natural. And so you see the red line, and this is what it can be done with photoluminescence spectrometer. Okay. Another natural pink diamond versus CVD diamonds. Again, you see the CVD is the red one. You see the difference in spectrum. Still, you have some of these peaks, but you are completely missing the silicon vacancy that, as I showed before, can occur in a natural diamond, 1 out of thousands, and is usually the fingerprint of the CVD synthetic diamonds. FTIR, the other vibrational spectroscopy technique. This is probably the most versatile instrument in the gemological laboratory. It is the instrument which has been used to classify diamond based on the nitrogen content, so type 1 versus type 2, and then the 1AA, 1AB, and so on. That was the technique used. It's the instrument for emeralds. It's not telling you only if the emerald is treated or not and with which kind of compound has been treated, but not only if it's natural or synthetic, but actually even kind of identify the manufacturer of the synthetic. I mean, it's so very precise. And it works a lot with even with organic material like amber, copal, and so on. So the Fourier transform infrared spectrometer, this is the origin of the acronym, is a mandatory tool, of course, and these are only some of the stones that can be used. So what we are using here, this is the visualization of the electromagnetic spectrum. This is a close-up of the visible from 400 nanometers to 700 nanometers. Then we have the infrared on this side and the ultraviolet on this side. So this is the only small part that we are using with the UV Visneer. With the infrared, we are going to use to expand a lot our capabilities of testing. Again, this is the visible that you can see in the spectroscope. This is the range that we can get it with the UV Visneer. And actually, this is the range that you get with the infrared spectrometer. So you have a lot of space to get a lot of new information, and of course they are super useful for us to identify plenty of not only stones, but even, again, treatments, synthetics, and so on. How it works? This is one of the techniques. You have a mirror here. The infrared beam make this path as bounce at 90 degrees. There are a stone here. The infrared beam crosses the stone, and only the absorbed part is not transmitted, and the transmitted part goes directly to the detector. Okay? Originally, this was the path, but sometimes the stone is too small to be arranged like that, so this was a different, This is the most classical setup, but nowadays we tend to use more this setup, which is called drift or sampling method, which is called drift, which comes from diffuse reflectance infrared Fourier transform spectroscopy. This method has been developed for the study of powders. So you had powders here, and then you were analyzing that. Only later, probably 20 years ago, it was found that it was super, super, super efficient for gems as well. How it works, the beam goes up, it's reflected down and focused downstairs by this ellipsoid. And then it's bounced back on the ellipsoid and then focused on the detector. So if we put a stone here, this beam crosses the stone and is reflected 2 times before going to the detector, okay? And so this can help even to get rid of the different refractions and so on due to the cut. I mean, this helps us a lot. So practically most of the FTIRs on the market nowadays work on this. You don't have to struggle with the orientation of the stone in this case, while you have the beam that we saw before, I need to orientate the stone in order to have the beam that passes from one side to the other one. And sometimes it's not easy. With diamond, what you're doing is to align the major facet on the crown with one on the pavilion, you know. But sometimes it's not easy, especially when you're dealing with small stones. With this kind of technique, you don't have to think about anything. Just put the stone on the sample stage and take the scan. And no matter what is the different resulting beam coming out from the stone, the ellipsoid is designed in a way that no matter what, it will be always focused on one point where the detector is. So let's go to the practical application, probably something that will be more interesting for you, starting from color stones. So we have this. This is a 10-pointer brownish something. I mean, any of you want to deal with this thing, you know, how much it takes to, you know, put on the refractometer, get rid of the extra fluid, you know, polariscope and so on, bang. This is an actinide. I mean, it's not something that you stumble on every day, and that's the problem, you know, because nowadays we are having on the market a lot of material that it was not available only 20 years ago. Because the good thing is going to be scarce, is scarce. There are not so many nice things, and so people have to invent some other things in order to sell, you know. And for many of these materials, we don't even have a refractive index at all. I mean, it's material, phosphosiderite. You know, these materials are crazy. Anyway, you can do the same even with FTIR, working with specular reflectance. So even here, you have the red line is our stone, the blue line is the stone coming from the database, and you identify the actinide. UV near spectrum is not so detailed as the Raman and the FTIR, but even in this case, I can do an identification. With photoluminescence, corundum is super easy. Corundum has an emission due to chromium. This is the typical doublet that every of you have seen in the spectroscope. Okay, here how it shows up is like that. And when you have something like that, you are sure you are dealing with a corundum. The bad news is that you don't know if it's natural or synthetic. That is a bad news. UV Visneer is the tool or the easiest tool used to identify the copper-bearing tourmaline. How you do it? I mean, here we have 2 different spectra of 2 tourmalines. One, it's a nice neon blue, but not Paraiba, not Elbite. In this case, you have manganese here, but most important, you have copper here. And this copper is showing off at 925, 930, 940 nanometers, which is in the infrared. It's something that we cannot see with our spectroscope. You remember it ends up at 700. So this is the only instrument that can help us to identify this material. Of course, there are more expensive and complex instruments. So we are talking about the base, the basic instrument that you need to identify this. This is how emerald origin was dealt with 30 years ago. Okay, so you have 4 spectra of 4 different emeralds. These 2 are, as you see, this is chromium 3, chromium 3. I mean, these are very similar. The main difference is about this band of iron here. And as you know, in Colombian material, you don't have it. So you have this line completely flat, no absorption due to iron. And you have in Afghanistan, and you have in Brazil, and you have so on and so on. So this was the basic, the absolute basic 30 years ago for the identification of the origin. But nowadays we have so many new sources, and so we have to deal with more complex problems that we have to face with other instrumentation. Again, gem identification, magmatic versus metamorphic. This is important because, as we will see later, if we have this important piece of information, we can use more useful information from the FTIR. So before running an FTIR on ruby or sapphire, to get more information about their treatment, what I need to know if they are coming from a metamorphic or a magmatic environment. And they are quite straightforward different. You know, this is the metamorphic one. You have this band which is responsible for the blue. Here you have this one, okay, due to iron. And this is the main difference that you have besides this one. But still you have iron 3 here. But this is the thing that you have only in the magmatic and not in the metamorphic. This is an interesting thing. We were in Sri Lanka exhibiting at the gem shows, and this guy came to the booth with this stuff, you know. That's a nice star, but it was super heavy. I mean, it was kind of 10 millimeters, but it was heavy, you know, very heavy. With this star actually was not super moving, you know, but it was there. I mean, as you can see it here. It was a damn cubic zirconia. And they made this stuff by abrading the surface. Trust me, it was crazy. It was a red cubic zirconia, cabochon, abraded on the surface with this, you know, tiny, in order to create the star. And this took, I mean, really 20 seconds, 30 seconds. Again, how practical Raman it is. Look at how much small is this pendant. I mean, it's 8 millimeter wide. You have to identify the green stuff. I mean, it's really less than 1 millimeter each. Okay, you have a guess. You can do it. How much time it will take to you to get there. With Raman, 20 seconds. 30 seconds. Time is money, especially for the labs. So they have to be quick. They have to identify material very, very, very fast. And again, this is tsaurite and has been, of course you have a clue. All of you thought about, oh, maybe emerald, maybe it's tsaurite, maybe chrome tourmaline or something like that. But you have to know it for sure. And this is tsaurite. This is another interesting story. An importer in Italy come to me with 2 of these things, 2 necklaces, with these big bulls, kind of 20 millimeter, you know, but they were mounted, you know. And the guy was saying, okay, I'm dealing with 2 different vendors. They brought me this stuff. I mean, I didn't took both photos, but they were very similar, not identical, but very similar. My problem is that I'm going to do a big order of this stuff, but I'm confused. This guy says it's variscite, and he's asking me $250 for a strand. The other guy says this is magnesite, and he's asking me $40. And you know, from your perspective of work, you have these beads, you cannot do practically anything. It's opaque with standard instrumentation. You can unmount the stuff, it's opaque. Right? And they were both magnesite. So the guy selling the variscite was cheating, practically. And again, 30 seconds. This is what I was saying before. Some of these slides that with FTIR helps a lot for the identification of some treatments in corundum. So let's start with this slide. And this one is probably, I mean, it's showing here, you're showing boehmite, kaolinite diaspora, here you're showing calcite. The story is that when these peaks are showing up in the FTIR spectrum of corundum, you can be sure the stone has not been heated above 800 degrees Celsius. Because after that, all these peaks disappear. They are nilled out, okay? The only problem is that the rule, it doesn't work the other way. If you don't have the peaks, it doesn't mean the stone is heated. Maybe there's no boehmite, there's no kaulinite, there's no diaspora. So it works only in one way. When you see them, great, the stone has not been overcooked. Okay, now we are talking about all these low heat treatment, whatever. So when I say heat treatment now, I'm saying about the traditional heat treatment that goes, I will not say completely dissolved rutile, but it goes up to 1,300, 1,500 Celsius. And for calcite is the same. This is a spectrum from unheated Mogok ruby. This is, I will not say a fingerprint, but it's very, very common for nice Mogok ruby to show up calcite when they are untreated. When you see something like that in FTIR, you can be sure that it's untreated. This is metamorphic sapphire heating in reducing atmosphere. You see this 3309 peak here with this group. This is called the 3309 group because this is the best one. So usually in a metamorphic sapphire, this is where it's important to know if the sapphire that you're testing is metamorphic or magmatic. So you have to run the UV smear first. So if you are dealing with a metamorphic sapphire, you should not have this 3309 peak. This is coming up after the treatment because there is a diffusion of hydrogen. Okay, and this peak is created. When you see something like that and the sapphire is metamorphic, it's more than an indication that the stone has been heat treated. Again, if you don't see it, it not automatically means that it's untreated. But the development is quite often like that. This works only for the metamorphic sapphire. So that's the reason why it's important to know before that. Again, if you have this 3161, this is typical from untreated pot parasha. When you have this kind of peak, you can be sure the stone has not been treated at high temperature, of course, at standard temperature. Okay? And that's even the reason why you have to have multiple instruments, because some of them are propedeutic for the solution and the use of the next one. FTIR is, as I told you before, the instrument for emeralds. As we can see here, we have 3 spectra. The green one, the stone is completely untreated. We are focusing on this area. This is the area that interests us, from 2,800 to 3,050 centimeters minus 1. This blue line belongs to an emerald that has been treated with oil, and this one to an emerald which has been treated with resins. So what we are seeing here, the typical flash effect of resins, and it's an old brownish oil inside these fractures, clearly shows up here. Of course, when you are identifying better the material, you are zooming in the spectrum because you don't need the rest one, but just to show you which are the difference in emeralds. Treatments. B-type jadeite, still due to resins. In FTIR, you have A-type, which are not showing anything, okay? And these two small peaks means that you have been bad and you have touched the stone with your fingers without putting inside, because those belongs to skin oil. Believe it or not, we found more than 5 or 6 different sources, written sources, where the writer described those peaks in diamonds, like something. But they are only your skin oil. What is important to see is that you have, just like in emeralds, you have these peaks developing when you have B-type jadeite. This can be done with Raman. We were talking about FTIR before. This can be done with Raman as well. As you see, the A-type jadeite has only this small Raman spectrum here until 1,100, and then it's dead flat. All these areas dead flat. When you don't have a dead flat, especially here and here, it means that there is something else, okay? And the most probably thing is resin, is polymers. So the main peak and the more important one is this one, 1,609 centimeters minus 1, but even this group is very important. It is important to understand that you can have a huge reaction from the polymers or very weak reaction. So between these two, they are both treated. But you see the 1,609 here is quite small. And here the group is very small. So it's very important when you're testing Raman with Raman jadeite to test in multiple position on multiple spots of the material, the bangle, the pendant, whatever it is, in order to be sure that the piece is not treated. I told you before, FTIR is the instrument for emeralds. And as I told you before, it's not only identifying the natural versus the synthetic, it even tells you exactly what kind of manufacturer did that. Based on, I mean, it's a real fingerprint. So this Molossi is an Italian guy that made this actually very similar to the Byron, is a hydrothermal synthetic emerald. Tyrus made a hydrothermal too, and actually what you see here is a spectrum that is very, very similar to the green one, which belongs to a natural emerald. What you see in difference is this peak here that you don't have here, and this group, of course, you shouldn't have a close-up. You know, this group is missing here in the natural one. The Chatham, or the flux in general, is the easiest one to check, because, you know, this dead flat, it means no water. All these groups shows up water. And when I have no water, because of course when I'm producing the flux material, I'm working in a closed environment without water, I don't have water. So it's the easiest spectrum, you know, to be identified. FTIR is the only instrument that can detect synthetic quartz. No one cares, because quartz is so cheap that no one gives a damn about that. But you really want to know if your amethyst is natural or synthetic, you have to go FTIR or some instrument more complex and more expensive. And this is the difference between the two spectra. Synthetic alexandrite, another very important material. So far, alexandrite has been synthesized only with the flux method. Okay, so when you do that, let's, for example, Chatham. When you do that, you have this kind of spectrum. On the contrary, when you have a natural one, you have this one. And it's pretty straightforward, you know, to identify. Again, when you have a nice loose stone, full of veils, whatever, but we are not talking about that. We are talking about 3 points pavé in, you know, mounted on jewelry or whatever. So again, it helps to save time. The bad news about Raman is that it's super to identify material, but it's very rare that it gives you a hint about the nature of the material. I mean, if natural or synthetic. Practically it doesn't, with only few exceptions. It's just like the refractometer. I mean, you have a reading for corundum, you don't know if it's a flux or vernal or a natural stone. With Raman it's the same. Basically it tells you it's a corundum, or I mean, it's a beryl. In the case of spinel, the situation is a bit different, because when heat is involved in the atomic structure, the crystal structure of spinel, you increase the disorder of the structure. And of course, heat is involved when you have a flame fusion spinel, you know? So what you have here is the Raman spectrum of a synthetic spinel, flame fusion specifically, but it's the same, others are the same. And here you have the natural. You see that the main thing is that you have an extra peak here that you don't have in natural, and you have a broadening of this band and a shifted towards higher wavelengths. So you make a distinction between natural and synthetic. But you can do it even with photoluminescence. What you are seeing here is quite similar to what you see in corundum. You have chromium showing up at 685.5 nanometers, okay? Practically in every spinel that I tested, I have this image in photoluminescence, okay? And when I see this, I know the stone is natural. And it's not only natural, even if it's natural, it's even untreated when I see something like that. A narrow peak, 685.5, and this group. Then you start to see these other spectra of other stones. When you start to include temperature in the structure, for example, in this cobalt diffuse natural, you have the broadening of the main peak, and you have kind of annealing of the others, okay? And as the temperature increased, the peak, the main peak, it becomes bigger and towards higher wavelength. So with photoluminescence, until I arrive to the synthetic, where it's here, and the other peaks are complete and nilled out. So with photoluminescence, I can indeed identify not only the natural and synthetic, but if I have a natural with inclusions of the natural, and I have the peak like that, I can even say that this stone has been treated. Usually it's, I mean, so far what I know, it has been treated besides the cobalt diffused by heating only the red ones to get rid of the brownish patch. So it's something that you are not thinking about when you have a purple or a blue spinel in front of you. Of course, blue could be cobalt diffused, but the red, the heated only are the red one. Fuck. Diamond. Okay, I'm already late. So this is the classification of diamond. I mean, really, again, type 1 versus type 2. And then you have the aggregation and so on. This is an FTIR, how a diamond, a type 1 diamond comes out. So based on the aggregation or a single nitrogen, you have this area. This tells me I'm a diamond. Okay? This mountains tells me I'm a diamond, and this tells me the aggregate that I am inside. Type 1 diamond have these aggregates, and these are explained, but we don't have time. When you don't have nitrogen, you have type 2A or type 2B that has boron. You see, this is boron contamination in type 2B, which are actually the blues. And when you don't have anything, you have that flat, you have the type 2A. The screening rules are, you know, vast majority of natural colorless to near colorless belongs to type 1 AAB. I mean, they have the nitrogen aggregates. Thanks God, most of them, they have it. And all the synthetic colorless, near to colorless diamond belongs to type 2A or type 2A plus minor type 2B. When I say plus minor type 2B, it means that in some HPHT material, they are boron doped, okay, to compensate the color. And so you can have in FTIR some peaks of boron. How the screening is done, it can be done based on 415 and 3. If you have it, you are safe. You have a stone that belongs to 96% of the stone that have all nitrogen. If you don't have it, you could still have a natural type 2A, but you have to use other technology to test it. This is fluorescence spectroscopy, which is based on the same thing. Testing for HPHT treatment. This is probably the most complex thing about diamonds still right now. Thanks God this material is almost not treated at all anymore, because their prices went so low that no one is interested anymore in having this thing. But again, the danger is there, because these stones usually are great, are huge, are high color, and are high clarity. So when they are stumble on the market, they are asked for lots of money. And so you see, for example, a natural versus a treated, some of treated one. You have developments of these peaks, which sometimes can be present even in natural. But for example, when you have this peak, you are safe. The stone has not been HPHT treated. It's not always the case. Again, I said, it's the most complex thing about diamond right now still, and even GIA sometimes sends back the stone and say, I cannot give you an answer about the origin of the color of this diamond. It's rare, thank God it happens rarely, but in that rare occasion, you have a stone that's practically, it's 15% of the Rappaport maybe. The type 2A plus 2B is the typical HPHT synthetic material, which a tiny, tiny pinch of boron. You know, you have this spectrum in FTIR, and you are almost sure that the stone is an HPHT synthetic one. Sometimes in CVDs, you have a prominent presence of this silicon vacancy peak, but sometimes it's very, very small. It depends by the purity of the gas used. The more the gas is pure, the more it's expensive, of course, and the less this defect shows up. So in the current production, especially from Far East, we very often saw this very huge peak of this silicon vacancy. Again, the importance of immersing the stones in liquid nitrogen, the same three stones. Below you have room temperature, and it's that flat, almost nothing. And then when I immerse them in liquid nitrogen, boom, silicon vacancy peak comes up, and the nitrogen vacancy peak comes up, and I can make the identification as a synthetic CVDs. Black stones, which are complex, especially when they are mounted. So diamond, as with Raman, it can be easily identified. Moissanite, black moissanite, can be easily identified by FTIR. One downside of Raman do not digest very well black stones because they are actually absorbing the Raman emission. Okay, so in that case, like in this case, we switch it directly to FTIR and we have this synthetic moissanite spectrum. Then you have cubic zirconia, something very, very much used, and then black spinel. Again, all of them identified by FTIR. The importance of the reference in data collection. You have your stone, you have the refractometer, you have the readings, and then what do you do with this? You have the tables, you have the values, okay? Exactly the same with the spectrometers. Topaz, by the way. You have the stone, you have the Raman, you have the spectrum, and then you have the reference. It's the same. It's exactly the same. So the operator can operate the instrument. Doesn't need to have a degree in anything if they have a reliable database. These are the last three I'm done. These are the last three more advanced instrumentation. When we are talking about elemental analysis with EDXRF, we are actually identifying the chemical compounds of our stone, of our material. We need to go even deeper, especially after the 2000 with the beryllium problem, because beryllium is an element so light that is not being able to identify by the EDXRF. Usually it stops with the sodium. You know, you cannot get the beryllium. And then all this instrumentation has to be implemented. I don't think that before 2000 GIA was using LACPMS. I don't think even LIBS. These are far more advanced than the EDXRF, but the big problem, and that's the reason why I put this red thing again, and they are violating the sacred rule of the gemologists. They, in order to work, they have to ablate a super small portion of the stone in order to ionize it and identify it. It means the stone, even if the spot is in the order of 40 microns, 30 microns, needs to be touched in some way, needs to be damaged. I mean, we'll say not damaged because usually they do it on the girdle, but it has to be done in both cases. So the only difference between the two is that LACPMS, it's more advanced. It can detect a lower quantity of ppms of all the trace elements. And right now, LACPMS is a lot used not only for the detection of beryllium in corundum, but mostly for the characterization of the geographic provenance. I mean, this is how it's done right now. We are collecting a lot of trace elements, put them together, and with the artificial intelligence, we are going to have some more precise mapping of the EDXRF. The basic use for EDXRF is the manganese content for example, versus strontium to differentiate freshwater versus saltwater pearls. This is something that has been done since many years now. One of the examples. LIBS is the most economic solution for checking beryllium. And here the girdle of a stone actually is a 60-pointer stone, so the girdle is small. And what you see here is the spot. Okay, is the spot that the LIBS, the laser of the LIBS hit on, and it worked, to ionize the material. And then we have the LACPMS, which is the mass spectroscopy. In this case, again, the sample needs to be ionized in some way in order to be then later analyzed and then come to the identification of various material. It's often not only the quantity of the material, because actually I forgot to mention that LIBS in LACPMS, they provide even a quantification of the elements, the trace elements, while EDXRF not, only qualification. But it's more a matter of ratios between elements. This is how it works now. So we have here vanadium versus magnesium. We have vanadium versus, I cannot read, what is that? Another element. I mean, what you read is to combine all these ratios between elements, and in the end, what you have is the characterization, especially for the geographical provenance. And this is a very interesting is the last one, thanks God, is the very interesting image that shows you that in this case, this sapphire, I think, yes, they were out of all this data, but when they started to have to put together to get the Kanchanaburi material and they tested it, it comes up that they were overlapping here. So the importance of the database, especially when the database is consistent, especially when the samples are coming from a real, I mean, the ideal solution will be to collect the stuff directly on the field, but it's not always the case. But database, I would say, is 50% of the equation. Without a reliable database, the instruments are telling you something that you can even not use at all. So the database needs to be consistent. Probably nowadays it's the most complex problem. You can, with the money, you can purchase everything you want. But for having samples, you have to send someone to the place in the hole to collect the stuff and so on. And this for many, 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 many stones. Thank you. Questions, but I don't know if we have time for questions. Hello, good morning. Yeah. 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 Yeah, I know. The problem is that what you have to get is the, as I told you, is the band at 870 nanometers. And it's, sorry? Oh yes, if there is any available, any handled UV Visnir for the detection, the differentiation between metamorphic and magmatic sapphire. And I will reply in that unfortunately the most important part of the spectrum is far above the visible range, is in the 860 nanometers. And it's not a matter of how much small you can make the spectrometer. You really need to have the light going in the, so, I mean, we produce a unit which is 4 kilo and it's smaller than a shoebox, you know. There are even other instruments on the market, even smaller than that. I can vouch on mine, and I can tell you that mine works. The others, you know, I let the other people to, you know, describe you if it works or not. But it cannot be too small because you really need to have the sample inside a controlled atmosphere in order to compare your result with the database. Otherwise, it's not working. It's not something that you are point and shoot, unfortunately.
GIA graduate gemologist
Yes.
that has the basic set
Yes.
of instruments,
Yes.
who understands to a degree the value of this additional information,
Yes.
but hasn't the equipment to obtain it, although the literature is out there. But what is your recommendation for that particular gemologist, an independent, does not work for a large company or a university? What would be your recommendation for the single upgrade in instruments under $20,000?
You know, to give an answer, it really depends what is the nature of your work. For example, we have clients who are only dealing in Paraíba tourmaline. So they don't need a Raman, they don't need an FTIR. They need an UV Visnir. You know, and only for doing that. With a UV Visnir, you can do plenty of things, but they need that for that, like he needed for the metamorphic versus the basalt. He doesn't need the FTIR, I mean, in the beginning. He needs something to solve that problem. So it depends what is your problem. For example, we have a lot of clients who are appraisers, and they are dealing nowadays with all these, I mean, necklace of, again, phosphosiderite or of magnesite, like you see it before. They need to do the appraisal. They don't have the instruments to, you know, tell what it is. Raman is perfect. But again, it's not telling you if it's natural or synthetic in many cases, you know. So it really depends what you, but the first thing, I am a gemologist, but I started as a gemologist. I mean, enthusiast of this kind of technology and so on. So I saw with Miko, we saw that this material, these instruments were not on the market. I said, you know what, let's make it. We start to make it for ourselves, for our use. Only later we decide, you know what, no one is doing, why not selling them, you know, and make it nicer and so on. So I hear what you say. The first thing is that the information is out there. Thanks God, all the gems in gemology are free, so you can browse them. The problem is that you cannot compare the information with your experience, and I understand that. I understand that. But again, I cannot give you an advice on which instrument is good for you unless I know what you should have all of them. And I know that people say, yeah, I know. But I have to start from somewhere where I should start from. Okay, that is the question. I have to talk to you to understand more what is your business, and then I can tell you, okay, maybe you need this or you don't need that, and so on. I mean, people come to the booth and say, I need beryllium, go away. I cannot help you. Go to buy, because to send it to GIA or whatever, or if you're full of money, buy a LIBS or LECPMS. I mean, it's not.
You talked me into buying a Raman. You weren't the first one that have done that.
Okay.
But how much for a Raman system that can do what your instrument does?
15,000.
I'm sorry.
Yeah, 15,000 euros right now.
All right, so before we get into all the pricing of all,
Yes, we are.
all of that,
I am late.
you can see Alberto. Is Nico here?
Yeah.
Alberto and Nico, they have a booth, a table right out here in the entryway. Look at all the equipment. It's great. Next question. Yeah.
Please.
So, I just wanted to say, I am a graduate gemologist. I do have a small home lab. I am independent. I'm a gem cutter. I deal with rough and cut.
We're twins.
Absolutely, you're cute. I dragged my feet for years. I got the Gemo Ramen last year. I bought it right after the show. It has already paid for itself. And it did that by me going through my old parcels of what I wasn't sure about. That was rough that I quickly tested. And okay, now I know what it is, I can cut it. But also I've had clients who, they wanted a lab cert, and I'm not a lab. But I would take the ramen, I could print it out, I could say, here it is. And then they would buy my stuff. And I like when people buy my stuff. I'm weird that way. But, you know how long it took me to fly that. And in, 8 months?
Oh, yeah.
I had to come back.
Any other questions? Comments?
Whoever has a question can join me at the booth. We are very happy to answer to everyone. Till Sunday, we are there, no problem. Available for everyone. You're very welcome.